In this video, I want to discuss the structure factor. Now, in a previous video, what we saw was we talked about diffraction from a crystal. And we came from our diffraction from a general object and said, in the case of a crystal, what we can do is we can break that object down into small unit cells and think about how we've got the electron density from the unit cell and then that translational periodicity across. And we said that when we broke that down, we ended up with our total scattering as the structure factor, which we said was the Fourier transform of what's going on in the cell, multiplied by this term here, which we said helped us produce the reciprocal lattice. Now, this breakdown, if we go back to what we were talking about in the crystallography section, we were thinking about how we might have the lattice structure, and the lattice structure, we then have a structural motif that we put on top of it. So while these two wallpapers have the same lattice, they have slightly different motifs. And if we come back to this, what we're saying here is, if you think about it, this is being produced by the lattice structure, which is defining the reciprocal lattice, but this term here, our structure factor, which is the Fourier transform of the electron density of the cell, is related to that structural motif that we're putting on top of it within each unit cell. So what does that do, and what do we get, or how do we then consider the scattering from the unit cell? So what we said is we had this structure factor here, which we said was the Fourier transform of the electron density within the cell. Now, in the same way that previously we said, let's think about it as the electron density of the cell convoluted with the lattice points, we can play a similar trick here and say the electron density of the cell we can think of as the sum of the electron density of each atom convoluted with a delta function which gives the individual positions of each of those atoms. So all I'm doing here is this is a mathematical expression saying basically defining the positions of each of the electrons within that unit, the positions of each of the atoms and the electron fields of those atoms within the unit cell. So that's what I've got here. So my structure factor is therefore the Fourier transform of this. Now, we can therefore do a little bit of maths and show, as we did previously, that the Fourier transform of two things convoluted with each other is the Fourier transform of one multiplied by the Fourier transform of the other. So we get this expression here. And so what we end up with is the Fourier transform of the electron density, which we call the atomic form factor here, f of n, multiplied by the Fourier transform of a series of delta functions, which just gives us this exponential 2 pi I r dot s term. And this is the so-called structure factor equation. And in fact, what we can do is we can then say, well, in fact, we know that R we could write as a series of coordinates within the unit cell defined by the lattice vectors A, B, and C, where X, Y, and Z here are atomic coordinates, so fractional coordinates of the unit cell defining the position within the unit cell. And S, we know, is going to be our scattering vector defined by our HKL here. And so we could put these expressions in here and do the dot product, and again the cross terms cancel, and so we end up with this expression here, the structure factor equation given by this. So why is this structure factor equation important? Well, coming back to what we had previously with this mathematical definition right back here, we said that the diffraction from a crystal, this defines the point, and then this is going to define the amplitude of the scattering that we're getting at that point. It's some sort of multiple. So this is going to determine how strong a particular scattering beam is. And in fact, what we can show is that mathematically, what we measure is the intensity, which is in fact going to be the modulus squared of this. So it turns out that the intensity of a diffracted beam is going to be the modulus squared of this expression. So this modulus squared. So if we calculated our structure factor equation here, and then worked out this f of s value, and then took the modulus squared of that, that would be the observed intensity of our diffraction spots, which is what we measure. And in fact, this is important and then affects what we're going to see in the diffraction pattern, because what we're saying here is that the atomic positions within the cell are going to be related to the intensities of the diffraction spots that we observe. And this is particularly important with things like one of the most obvious ways of this is how this then links to the symmetry of the cell we observe and what that does to the diffraction pattern. So let's take, for example, something that is body-centered cubic. So if something is, or just body-centered in fact, so if something is body-centered, it means that we have pairs of atoms, one at x, y, z, and one at x plus half, y plus half, z plus half, as shown here. If you put this into the structure factor equation and say rather than summing over all of the atoms, we're going to sum over pairs of atoms, then in fact mathematically you can then take out this term here that looks like 1 plus exponential pi I h plus k plus L. Now you can work through the full maths of this to make sure that you're happy with it, but the key thing here is we've got this expression in our equation. And if h plus k plus L is even, then this term, this exponential, is going to be equal to 1. So this is going to be 1 plus 1 is going to be equal to 2. So this is going to have some multiple of 2 multiplied by whatever is taking place here. But if this is odd, h plus k plus L is odd, then this term becomes equal to an odd multiple of pi I. So the exponential is going to become equal to minus 1. So this is going to be 1 plus minus 1, which is going to be equal to 0. So we've got this term multiplied by 0, so our entire structure factor equation becomes equal to 0. And the consequence of this is that the beam is going to disappear. If h plus k plus L is odd, then this beam is going to disappear. And therefore we are not going to see it in the diffraction pattern. And so this is really important for us to understand, is that because of this structure factor equation, if we have certain symmetries within our pattern, it will cause certain beams to appear or disappear within the pattern. And so we would expect within our diffraction pattern, if we have something that is body-centered cubic, we don't see any diffraction spots corresponding to HKL, corresponding to beams where h plus k plus L is equal to an odd number. Those beams will systematically disappear. So for example, our 1, 0, 0, we would see no diffraction from. Our 1, 1, 0, we would see diffraction from. Our 1, 1, 1, we see no diffraction from. Our 2, 0, 0, we see diffraction from, and so on and so forth. So this is really important to understanding which peaks we expect to see in a diffraction pattern and which ones we don't expect to see in a diffraction pattern. And more important, importantly, when we get on to thinking about our powder diffraction refinement and factors that affect various elements of our powder diffraction pattern, we will see that the intensity is therefore related to the atomic positions by the structure factor equation. And therefore, if we want to change the intensities of peaks in our diffraction pattern, we need to consider our atomic positions are one of the factors that could potentially affect that.